Hello. Now in fifth lecture we are going to do many different things as far as application of congruence is concerned. But before that, in lecture 4 we have proved all the tests of congruences. First, in lecture 3 we have assumed that SAS is a test of congruence which is postulate and cannot be proved, and in the next lecture, that is fourth lecture, we have proved ASA, SAA, SSS and RHS, these 4 tests. So total 5 tests of congruences are there. Then the question comes is, why ASS or AAA is not the test of congruence? This is very important to understand, because majority of the students remember why 5 tests of congruences are there, what are they, but nobody thinks on the remaining 2 combinations, 2 sides 1 angle when the angle is not included, and all the 3 angles. These are the 2 combinations which are remaining, are not considered as test of congruence. Why? Let us look at the reasons of these 2. As far as AAA is concerned, it is very simple. If I provide information that one angle is 30, another angle is 50, and the third angle is 100, if I give information about only 3 angles and no information about side is available, everyone can draw different triangles. So that is the reason why AAA cannot be considered as test of congruence. By given information, the 3 things that we are going to give, if we can construct a triangle which is unique, anybody constructing the triangle using that information gets exactly the same triangle. If that happens, we will consider the test, that information as test of congruence. However, if we get even more than one, only 2, by the same information, if we get 2 different triangles, we are not going to consider it as test of congruence. However, in AAA we can get infinitely many triangles with the given information, and hence AAA is not the test of congruence. As far as ASS is concerned, now let us look at this example. Suppose first angle A is given, say for example 30 degree. Then another side is given, say for example 6, and we got the point B. Now as far as third side, because this sequence is important, angle, side and the third side will be given. Suppose we get information about third side, say as 5 or something, 5, then this triangle with this side 5 as well as this triangle with this side 5. So if we take 5 distance in compass, put our still point at B and try to cut this ray using that distance, we are going to get 2 distinct points at a distance 5 from B, which are on this ray AC, supposed to be ray AC, and hence information given 30 degree, 6 and 5, which is ASS, gives me 2 possible triangles. One is this obtuse triangle and another this acute triangle, and therefore ASS is not the test of congruence, because we might get more than 1 triangles with the given information. However, RHS is our test where actually 1 angle and 2 sides is given. R, right angle, which is angle, H means hypotenuse, and one of the 2 sides. So ASS information is given, and therefore it is a special case of ASS where angle is 90 degree. So even if we want to cut this ray, say AC, 2 times, we cannot do it. Therefore, if the angle is 90 degree, RHS works. But for any angle, without thinking, if we start using ASS, maybe we will be in trouble in situation like this, and therefore ASS cannot be considered as test of congruence. So it is important to know which tests of congruences are there and which are not, and why are they not. Okay. Now the next thing that we are going to do is we will prove perpendicular bisector theorem number 1, which is if a point is on perpendicular bisector, then it is equidistant from the endpoints. Then we will prove converse of that. That means if the point is equidistant from the endpoints of a line segment, it is on perpendicular bisector. And the next thing that we will prove is concurrency of perpendicular bisectors. So these are the applications of congruency that we have learned so far. If any point P lies on perpendicular bisector of a segment, if any point P lies on perpendicular bisector of a segment, then it is equidistant from the endpoints. So given P lies on perpendicular bisector of segment AB, to prove that PA equals PB. Now this is perpendicular bisector, so therefore these two segments are equal. This is 90 degree. We may give name to this point as M. Now I give you sufficient time to prove this test, prove this result independently. Pause, think, it is simple, do it. Now we will not spend a lot of time in writing the entire proof. We will just try to find out which congruency test is going to be applicable. I think we have done this problem earlier. This is equal to this, AM equals BM, angle AMP equals BMP equal to 90 degree. These are given conditions. And the third thing that we need to find out is PM congruent to PM, which is common side. Therefore by SAS will give us triangle AMP congruent to BMP, triangle BMP. This gives us PA congruent to PB by CSCD. So the most important thing in this is SAS. You just identify the test of congruence and finish the problem. Okay. Next is converse of this. The converse of this statement would be whatever was to be proved here is given and whatever was given here is to be proved. Now given PA equals PB. So a point is such that it is equidistant from the endpoints of segment AB. PA equals PB. We need to prove that P lies on perpendicular bisector. To prove that P is on perpendicular bisector of AB. Okay. I give you sufficient time to think. Pause this video, think about it. There are more than one proofs. Find your own and then look at the video. Okay. One way of dealing with this problem is to start with, now we have two things to show. A line which is perpendicular and it is bisector. A segment is drawn, there are many perpendicular lines which can be drawn. A segment is drawn, there are many bisecting lines can be drawn. So now we want to find out a line which is perpendicular bisector of AB and hence it is going to be unique. So we deal with this problem by assuming or maybe by constructing midpoint of AB M. So point M bisects AB. That is what we assume, and then we join a PM. Hence we get two triangles. Now that is what is the situation for congruency of triangles. We get two triangles AMP and BMP. Now they will be congruent triangles. The only difference in this and this is that the test of congruence will be different. So if you look at it, this is what by construction these two lines are equal by, which is given condition, and again PM is congruent to PM, which is common side, therefore two triangles are congruent by SSS. So if two triangles are congruent by SSS, then corresponding angles will be congruent. AMP will be congruent to BMP, and because AMP plus BMP is a linear pair, we get each of them 90 degree. This need to be written properly. It is given in the notes, you go through the notes, but you need to develop your own habit of writing these proofs completely. If I keep writing it on the board, it will be a long video, not necessary. So we have seen how to write a congruency proof earlier also. I am now giving you the solutions of these problems. So one way of dealing with this problem is to construct midpoint of AB, convert these two triangles into SSS and show that they are congruent. And once they are congruent, these two angles will be equal. Then linear pair property, if we use, we can prove them 90 degrees. Another approach could be from P I drop perpendicular. PAB, and we drop perpendicular and let it intersect at M, and then this is perpendicular 90 90. Now again I get two different triangles. Now this length is equal to this length is to be proved. MA is equal to MB is to be proved. However, this distance is equal to this distance is given and a perpendicular is drawn. Therefore, now I have 90 degree hypotenuse these two and a common side PM. Therefore, RHS test will give me congruency here, and once I get the congruency, I can by CSCT I can say AM is equal to BM. Okay, so these are the two different approaches for getting this proof. Because we wanted to prove that perpendicular bisector, in first we assumed that the line is bisector and proved that it is perpendicular. In second we constructed perpendicular and then proved that it bisects. Only problem in this, which is a classical problem or a rigorous thinking if we do for RHS in this particular proof, one can ask a question. If you drop perpendicular from P onto segment AB and if it does not intersect AB, in that case you will not be able to take that point M and create two distinct triangles. So if you cannot create two distinct triangles, then there is no question of proving them to be congruent, and hence at that time we will not have sufficient tools to argue and say that perpendicular from P will definitely intersect AB. Requires more rigorous treatment, which is not in our scope right now. However, it can be eventually proved if we get into that rigor, but for time being we will assume that perpendicular from P on B, AB will intersect AB. So if that assumption is true, then this proof is correct, and hence this can be done by two different ways. Now therefore this first result, if P lies on perpendicular bisector, then it is equidistant. We normally denote it as PB1, perpendicular bisector theorem number 1, and we just shift these two conditions. What was to be proved is given in the second, and what was given in the is proved in the second, then it is called converse. And if we denote converse by PB2, then these are the two converses. In this case both of them are true and have been proved. Therefore we say that this result is if and only if type result. Okay, now let us use this result to prove concurrency of perpendicular bisectors. In any triangle, if we draw perpendicular bisectors of three sides, we find that they are concurrent. ABC. In triangle ABC, if we draw three perpendicular bisectors of three sides, then we find that they pass through a common point, which is very rare. If we often draw three lines in two-dimensional plane, it is very rare, it is going to be very rare probability that they are going to pass through a common point. In case of triangle, if you happen to draw three perpendicular bisectors, they are concurrent, they pass through a common point. Now, of course, this result can be proved by the things that we have discussed earlier, that is the hint. I give you sufficient time to think about it. Pause this video, think, get your own solution, or else look at our solution. Okay, now we will start with, let U be a perpendicular bisector of AB. U is perpendicular bisector of AB. V is perpendicular bisector of AC. Let this be U, let this be V, and let them intersect each other at P, and we are not drawing perpendicular bisector of BC. The strategy is you draw two lines, get the point of intersection, and prove that the point of intersection lies on the third perpendicular bisector. Okay, so now U is a perpendicular bisector of AB, V is a perpendicular bisector of AC. They intersect at P. To show that P lies on perpendicular bisector of BC. Perpendicular bisector of BC. Okay, so the challenge here is, because U is on perpendicular bisector of AB, if we join PA and PB, PB1 implies PA equals PB. V is a perpendicular bisector of AC. P lies on V, therefore PA perpendicular bisector theorem number 1 implies PA is equal to PC. So now suppose we call this statement 1, this statement 2, then 1 and 2 imply, now you can observe that PA is equal to PB and PA is equal to PC, therefore 1 and 2 imply PB equals PC. So now these two distances are equal, and therefore this implies by PB1, PB2, that is perpendicular bisector theorem number 2, P lies on perpendicular bisector of BC. So it is that simple. Provided we have these two tools developed, perpendicular bisector theorem number 1 and perpendicular bisector theorem number 2. If we have got those proofs with us, we can easily prove that concurrency of three perpendicular bisectors. This is very interesting proof. Use perpendicular bisector theorem number 1 two times, PB1, PB1. Then because of there are three quantities and they are equal, therefore we get PB is equal to PC, and because P is equidistant from B and C, we end up getting third perpendicular bisector also passing through P. Therefore P is a concurrency point. This theorem we abbreviate as CAP. CP, concurrency of perpendicular bisectors, CPB. Okay, now similar results, the way these results are available for perpendicular bisectors, similar results are available for angle bisectors are also. So, but before that, what we need to really define is what is distance of a point from a line. Distance of point from line. Now, suppose this responsibility is given to us to define distance of a point from a line. There could be many ways to measure distance from point P and line U, but you all will agree that the unique distance will be perpendicular. So we will also consider this as a notation, that if I want to find out distance of a point from a line, I will draw perpendicular from that point on that line, and then whatever foot of perpendicular from that point, that distance will be the distance of a point from a line. It is by using Pythagoras theorem we can easily prove that this is going to be the shortest distance, because if we take any other point on line U, it forms right angle triangle and it is going to be hypotenuse. Hypotenuse is always going to be greater than any of the two sides. Therefore, PM will be always the shortest distance. There will not be any other point on U which will give us smaller distance than PM. So this is important. Now, angle bisector theorem number 1. It says that suppose the point is on angle bisector of segment AB, point P is on angle bisector of angle ABC, then it is equidistant from the arms. So if now P is equidistant from BA and P is equidistant from, so distance of P from BA and distance of P from BC, they are equal. So we are supposed to draw perpendicular as per the definition that we have decided here. Let those 2 points be PM and PN. So given P is on angle bisector of angle ABC, to prove that P is equidistant, or in this diagram what we can say is PM equals PN. Now it is given that this dotted line is angle bisector, so these two angles are equal. Now this is a ready-made situation, so you pause the video at this point, try to think about why PM will be equal to PM, and then think about it, write your own solution, pause this video and check, otherwise afterwards check our answer. Okay, now it is obvious that we have produced two different triangles and they have to be congruent. If they are congruent, then PM will be equal to PN. So what are the elements that we have already got? We have these two angles equal, we have these two angles 90 degree, and there is a PB which is common side. So side angle, so by SAA, these two triangles will be congruent, and by CSCT, PM will be equal to PN. What will be the converse of this? To prove given PM equals PN, to prove that P lies on angle bisector of angle ABC. Okay, so in this situation we have been given angle ABC and P is such a point that it is equidistant. So from P perpendiculars are already drawn and it is given that these two. So what we are supposed to do and how do we prove converse? Again, pause this video, take sufficient time to prove it and look at the solution afterwards. Thank you. Okay, so I hope you have solved these problems. First thing that you need to know is join PB. We get two different triangles. And now we are supposed to prove that the line PB that we have drawn is angle bisector. We have dropped perpendiculars from P on the arms, that is what is the definition of distance, and hence we have PM is equal to PN, PB is equal to PB, and perpendiculars are drawn 90 degree. So which is the test that will be applicable to show these two triangles congruent? It is RHS. RHS test will give us these two triangles congruent, and therefore by CACT corresponding angles of congruent triangles, we will get these two angles congruent. So again, angle bisector theorem number 1, which gives us what property? If P belongs to angle bisector, it is equidistant from arms, and angle bisector theorem number 2, which gives us the property if P is equidistant from the arms of any angle, then P lies on angle bisector. So once we are done with AB1 and AB2, we will also prove that if we happen to draw angle bisectors of all the three triangles, then they pass through a common point. So in triangle ABC, if we draw angle bisectors of angle A, angle B and angle C, they are concurrent. That point is called incenter. The point of concurrency of perpendicular bisectors is called circumcenter. So this is the property that we will get, concurrency of angle bisectors. Now again, because we have proved perpendicular bisectors concurrency, I give you sufficient time, pause this video, think about this and then look at the solution. Solution is very simple. Again you go for only two angle bisectors. Let U be the angle bisector of B, let V be the angle bisector of C, let them intersect at P. Then the property that we get, drop perpendiculars from P on BC, on AC and on AC, we get these angles 90 degree. So if P belongs to U, then LMN. So if P belongs to U, then PL equals PM. If P belongs to V, then PL equals PN. Now these two results will give us PM equals PN. Now PM equals PN, that means P is equidistant from the arms of angle A and hence angle bisector of A also must pass through point P. So the results that we have seen today as far as perpendicular bisector theorem number 1, theorem number 2 and immediately concurrency of perpendicular bisectors, angle bisector theorem number 1, theorem number 2 and concurrency of angle bisectors, applications of congruency resulting into giving us two very good, very interesting concurrency proofs. These are absolutely important as far as our further treatment to geometry is concerned. They are basic results, everyone need to know them. If you have understood, try to practice on your own, check whether these proofs you can do it independently or not, solve all the problems given under lecture number 5 and there are 7 problems. If any difficulty, please contact us. Hope this lecture you find it interesting. We have got many results proved in this particular thing, so you can watch this video many times, pause, try to understand everything and make best use of this facility. Thank you. See you in the next lecture.